I want to do a quick just review, and I don't know that it has this in your book necessarily, but I want to do a quick review about why is it that our atomic masses up here are decimal places? Why is it that our atomic mass for magnesium, let's say, is 24.31? If atomic mass is the mass of protons plus neutrons, why is it that it's a decimal place? Yeah. Bingo. It's the average of all the isotopes. Average of all the isotopes. So there are multiple isotopes of magnesium, and one of them maybe has an atomic mass of 24, one of them maybe has an atomic mass of 25. We don't really know. The isotopes could be 22 and 25, right? 22 and 26. I don't know what the isotopes are, but we know that the average, okay, the average atomic mass, that is what we see. Okay, and it is the weighted average of all stable isotopes. Okay, the weighted yes, Tony.
So are we able to isolate isotopes?
To be able to study a single isotope? Or what do you mean? What do you mean when you say isolate? So if I ask you what do you think what is aluminum's most stable isotope? Most abundant, I guess I should say that. What's aluminum's most abundant isotope? Yep, it's gotta be 27. And we know that because that's what our atomic mass is closest to. So it's gotta have an atomic mass of 27 AMU. Right? And so its next most abundant isotope has to have a mass smaller than 27. We don't know if it's 26 or 25 or 24, whatever it is, but it's pulling that weighted average down. And so that means its next most abundant isotope is less than that. So does that kind of make sense? Is that memory coming back about why that is a decimal place? Okay. All right. Very good. So today we're going to get a little bit more into the periodic table. So I need you to have your periodic tables out. I'm not sure that we need to annotate on our periodic tables like we did in Chem 1, shade the metals, non-metals. I don't think that's the practice that we probably need to do. What I think could be a good practice for us is to draw in that stair-step line. Do you remember that stair-step line that goes down your periodic table? Okay, I'm going to get that. I'm going to show this periodic table up here on... I'll put this up on our slide too. This is from our book. Okay, so that's from the book. And so there's a stair-step line that you can draw in. Okay? And what does that stair-step represent? The separation between what? Metals and nonmetals. Like the true separation between metals and nonmetals. What are the elements that usually surround this right here? What are the ones that usually surround the stair-step? Metalloids, right? Those are the elements right in here that kind of are that blurry line, right? But if we're talking, if we need a firm line, that's what that stair step is for. So we know everything to the left of the stair step is what? Metals, right? Metals make up a vast majority of the periodic table. Non-metals are here. If you can't remember, just pick an element. The elements that kind of surround that stair step are the metalloids. And what's different about metalloids? What do they do? That's right. They behave like both, right? They have characteristics of both. And so sometimes they behave like metals, sometimes they behave like non-metals, all that kind of stuff. Let's recall, how do we organize the periodic table? Oh, sorry. Go ahead, Hope.
What's the deal with hydrogen?
Okay, so why does hydrogen sit in group 1? It has one what? Okay, one valence electron. One valence electron. It has one valence electron. But is it a part of this metal group right here? No, because it's not a metal. It's a non-metal. It sits over here only for that purpose of it having a +1 charge, number one, and it having one valence electron. That's the reason it sits over there. Sometimes you'll even see on some periodic tables, hydrogen sits right here by helium. Okay, so it goes 1, 2, then over. But for the most part, it sits over there. how do we organize or how do we label our periodic table? When we talk about the periodic table, what's the most common way that we need to identify the area of the periodic table we're talking about? Okay, we do talk about SPDF, okay, but we also talk, what's another word for families or columns? Groups, right. We talk about them most of the time in groups. And we label groups. How did we label them last year? 1 through what? 1 through 8 or 18. So remember how we say this is group 1, group 2, and it goes all the way to 18? But remember how the middle guys don't follow the rules? Okay, so I like to label them 1, 2, 3, 4, 5, 6, 7, 8, because that shows us our valence electron patterns. So on your periodic table, if you want to annotate that, you can. That's my, that's kind of my preference, is that we can see that valence electron pattern. But you also need to understand, like, there's two appropriate ways to label. You'll notice right here, if you look, it says it's group 1, and then underneath it says group 1A. Okay, so the 1A, 2A, then we pick up at 3A, 4A, 5A, 6A, 7A, 8A. That's another way to label it, where we skip those middle 10. Okay, so that's kind of my preference on how we talk about group numbers, right? But if you want to go and label that, this would be 1, 2, 3, 4, 5, 6, 7, 8. Okay, and that shows us the number of valence electrons in that particular group. Okay, so what does that mean for us? How many valence electrons does phosphorus have? How many valence electrons does phosphorus have? 5, right? How many valence electrons? It has 5. Very good. What do we call the rows on the periodic table? Periods, right? They're called periods. We don't talk about them very often because it's more likely for us to talk about what's happening in a group. The elements that are found in a group, what do? Elements that are in a group, do they behave alike at all? Yes, they do. They really do. Elements in a group behave similarly. Elements within a group behave similarly. Do elements in a period behave similarly? Not so much, right? Maybe a little bit at the beginning, but if I look at this period right here, potassium and krypton, no way do they behave the same, right? Krypton is a noble gas. It does not want to bond. It has a complete octet, whereas potassium wants to bond with everything, right? It wants to give that one electron away, and it's a metal, right? Number one, it's a different state of state of matter at room temperature. It goes through all of them. So we go all the way from solids. I don't know that any of these are liquids at room temperature, and then we get to gas. There's not very many elements that are liquid at room temperature. Did you know that? Very few. Okay, not that many at all. Like I want to say like 5 or less that are liquid at room temperature. Okay. All right. Where are the noble gases found? Where are the noble gases found? Very last group, group 8 or 18. Okay, very good. And what's special about the noble gases? They what?
They don't have 0 electrons.
No, not that they have 0. They have a full. So they don't want to bond because they have 8 full valence electrons. Bless you. So you're right. They don't want to bond with anything, but it's because their shell's already full. All right, let's move into naming compounds. This is one of my favorite topics. Okay, I love chemical naming. We're going to get started kind of right away with ionic naming. We did this last year, but like I said, I was gone for part of it, so I think you guys are pretty familiar with it, but we're going to dive a little with just some tougher examples probably. Let's start with ionic naming. What's ionic molecules between a what and a what? Metal and a non-metal. We are concerned with charges, right? An ionic compound has to be neutral. Okay. I'm not going to give you the rules for ionic naming. We're going to jump into some examples, and if you need me to articulate the rules further, I will, but I think you'll remember them kind of as we get going here. So let's say that I wanted the name of this molecule. CaO. CaO. This is called a binary ionic compound. Why is it called a binary ionic compound? It's just made up of two elements. Binary ionic compound. One's a metal, one's a non-metal. Okay, so simple naming there. So what would you give me? What would the name be for this one? Calcium oxide, okay? So if we remember the rules here, the first element keeps its regular ending. Second element always ends in IDE, right? Let's review here. Any anion that's just the element itself ends in IDE, right? So all of these on our periodic table of ions are IDE because it's just the element. Okay, so element by itself that has its negative charge is an IDE. All right, first one gets its name, second one's going to get an IDE unless it's a polyatomic ion, then it keeps its name, right? The polyatomic ion keeps its name. Did you guys look over your polyatomic ion flashcards or finish them a little bit at least? Okay, I'm thinking the quiz for that, the polyatomic ion quiz will be next Tuesday. Okay, so we don't have school on Monday, so I won't see you Monday. We'll probably do that quiz on Tuesday. So polyatomic ions, we'll start getting kind of familiar with them. But let's say I give you this, one, Mg3PO4 2. Magnesium what? Phosphate. Good. PO4 is phosphate, right? So we worked through this. Do you want me to show you how we got to that formula? Or are we good with that? Magnesium phosphate. It is. Every element starts with a capital and second letter is lowercase.
When you're naming it, like.
Oh, it doesn't matter. No, the written name doesn't matter. Yeah, capital or lowercase. Good question. Okay. All right, give me the chemical formula for copper 2 sulfate. Copper 2 sulfate. I want you to give me the chemical formula for that. Do you remember what that Roman numeral stands for? It tells us the charge. Good. It tells us the charge of copper or of sulfate? Just copper. Good. It tells us the cation's charge. Sulfate's one that we need to memorize, so it's probably not on your sheet. Probably got marked out. Okay, copper is a +2. What do we know about sulfate? It's SO4 -2. And so when I crisscross those together, or can you just see that they're going to balance? Right, they're going to balance. And so I'm going to end up with CuSO4. Okay? Would this be valid? Nope, we can't. It has to be reduced. Ionic compounds have to be reduced. Here's why. If we had a formula like this, it goes into a chemical reaction, and on the other side of the chemical reaction, it gets reduced, right? We're never going to be able to balance that, ever, right? The reaction will not balance if we're saying we're putting in 2 coppers and 2 sulfates, right? And that's not happening on the other side. So you've got to make sure that that's getting reduced. Otherwise, it's just not going to balance, right? It won't happen. Okay, give me the written name for this. Give me the written name for that formula. All right, what do we think? Good, tin, 4 oxide. We feel comfortable and we get the 4 right? Right, how did we know it was the 4? Okay. You all said things that I assume were right, so we're just going to go with that, okay? I knew it because I know I had to have 2 oxygens. 2 oxygens makes a -4 charge, so tin had to be a +4 charge. So I think maybe that's what you were articulating, okay? If you reverse the crisscross, that's not oxygen's real charge, so figure out what it needs to be and then figure out how to make it balance. So very good. Do we feel comfortable with ionic naming? You guys jumped right back into that, no problem. Okay, very good. What's the difference now with covalent naming? Good. Covalent naming, we are going to use the prefixes. What's covalent naming between? A covalent molecule has what? Two nonmetals. Good. We have to use the prefixes. Do we need to write those out, or do we feel comfortable with those? You kind of remember what they are, at least up the first four, right? After that and whatever, but mono, di, tri, what's four? Tetra. Good, very good, tetra. And then it just goes with regular prefixes, so penta, hexa, hepta, octa, whatever. I don't know what 9 is, nono, and then deca. So after that first four, you can kind of look it up. But covalent naming gets these rules. So let's figure out what this one is named. NO2. Nitrogen dioxide. Nitrogen dioxide. So rules again. First one keeps its regular ending. Second one gets an IDE. Now, why didn't my first element get a prefix here? There's only one of them. It's not going to be mono nitrogen dioxide. If there's more than one, it does get a prefix, but not if there's only one. Okay, so this one would be called P2Cl3. What would we call it? Diphosphorus trichloride. Diphosphorus trichloride. Okay, very good. Regular ending on the first one. Second one gets a prefix and an IDE. Uh-huh. Yep. So covalent compounds, metal and a non-metal. Non-metal. They're both negative charges. So they're going to end up sharing electrons. It's not a give and a take where they have to balance. They share those electrons. So we're not going to be concerned with charge. Yep. Okay, yeah.
If the ending element is like alone, if it's one,
It's still mono. Yep, like CO is carbon monoxide. Yep. Do you remember kind of the speech and spelling rule with covalence? If the element starts with a vowel, what do you do with that prefix? You kind of remember that? So this one, let's see. Look at this one. CO is called carbon monoxide, not monooxide. Okay, so you drop the O and the A off the prefix. The O and the A get dropped off the prefix if our element starts with a vowel. That's just like a speech kind of thing, right? Just for pleasantry, I guess. Okay. Tell mixture of ionic and covalent. So I want you to give me the formula for cobalt 3 hydroxide. I want you to give me the name for that one. And I want you to give me the name of that one. Like that?
yeah.
There we go. That's a big deal. Why is that a big deal?
Because it would change
Yeah, it would change the total composition. Without the parentheses, we only want 3 hydrogens. But with the parentheses, we want 3 of the OHs, which is what we need. Okay, very good. All right, Oni, what'd you have for the second one? What was the name of that second one?
calcium phosphate.
Calcium, then what?
Phosphate.
Phosphite. Very good. How did we know phosphite?
Because it's 3 and not 1.
That's right. Phosphate is PO4. So one less oxygen has to be phosphite. Very good. Okay, good. Last one. Tony, what did you have on the last one?
Carbon tetrachloride.
Very good. Carbon tetrachloride. Perfect. Okay, you feel good about that? All right, we're going to do a little gim kit here to practice with naming. Do you want to do the capture the flag one?
Yeah.